Maybe not so much. Okay. Yeah, it'd be nice. That would have to. I see, but I know, but then it's like everybody reaching into the same candy jar. Have Charles hand it out so he can come to class. I like that. No, you know what his jokes are? This is the joke he told me yesterday. He says, knock, knock. Who's there? Cow. Cow who? Moo. Then he goes, knock, knock. Okay, who's there? He says, interrupting cow. Y'all know the interrupting cow joke, right? As soon as you try to say cow who, interrupting cow who, he interrupts you with moos. But he does that then like 6 times in a row. So if you want to hear the same bad joke many times in a row, he is cute. He is cute. I will give him that. He is Lloyd, the Green Ninja from Ninjago. And we had, I got him the thing that fits the swords on his back, you know? And so he like pulls out his swords and he's got little daggers that come out the sides. And so we have sword fights in the living room. And yeah, he's pretty excited. And his mask, his costume comes with a mask, like it's got a ninja mask. So it's perfect. He's good. All right. Okay, so attendance is open. I didn't open the session. Oh, I think I still left it in, I just opened that in 4T instead of 5T. I'm gonna have to go fix 4T. They're gonna be all over me. They're gonna be like, you had an extra question at the end. Okay, it's now open. Try this again. Yes, I don't know what we're gonna do about Halloween. I don't know. It's gonna be kind of sad. All right, what number did we leave off on? We were 8 like 8.20 or 8.18? No, we're on evens. Because we didn't quite finish section 3, right? Were we on 8.18? I forgot to write it down. So we did finish section 3. So we're on section 4. Woohoo! Okay, we did better than I thought. We're awesome. We're great. Okay, y'all ready for y'all joke? All right. What do you call a fake noodle? An impasta. How did y'all know that?
I feel like that's like a common.
I had never heard it before. I was like at the dinner table giggling, and Charles was like, whatever. Like he's cooler than, I don't know, cooler than my bad jokes, but that's okay. All right, so before we go and do clicker questions, you have something due tomorrow. What is due tomorrow? Chapter 8 homework. Now this is really weird, right? Because usually we end on a Thursday and then you have Friday, Saturday, Sunday, Monday before the homework's due. It's due tomorrow, okay? Please do it. It's got those extra bonus points. So if you're trying to bring up your homework grade, you have the chance to do that, okay? So please get that homework done. Okay, so clicker questions. Ooh. Here are my clicker questions. All right, how far do we go? Here we go, this one. All right, everybody checked in? We only got 31 today. Oh man, 33. Well, come on, y'all, because I'm going to start clicker questions. I'll give y'all till 3 minutes. Okay. All right, so here's our first clicker question. Which of these is a colloid? Be careful you know the definitions between a solution, a suspension, and a colloid. Be careful with this. Shouldn't yawn yet. 10 seconds. It's too early in the day for that. Did we have like 40, 43 people? I mean, just click in. Okay. So let's go through each one and determine what each one is. Ampicillin, a liquid that must be shaken before use. If it has to shake before use, that means it's settling. What's the name of something that settles? A suspension. Okay. Pedialyte, a clear liquid. This should be a giveaway. It's clear. It is a solution. A fruit and yogurt smoothie, a chunky, thick, turbid liquid. What's the definition of a colloid? It's not transparent. What else? Won't settle. Why won't it settle? That's right. Why won't it settle? Small what? Small particle size. Right? It has things inside of it that won't dissolve. So it's not transparent, but it has small particle size. So if I said yogurt, what is yogurt? Yogurt is a colloid. A fruit and yogurt smoothie is not a colloid. Why is it not a colloid? Is that a small particle size? No, you can see when you have a smoothie, right? If it's chunky, you can see chunks of stuff in it, right? If you leave it long enough, it's going to settle. So this one is a suspension. How is a suspension? Lemonade, a cloudy liquid. A what? This is a colloid. Y'all saw yogurt and said that's a colloid, right? I know. Don't do that. Don't do that. Read the whole thing. Okay, what's vinegar? A clear liquid. A solution. Okay. Please, please, please read the whole thing. Because if you had gone on to D, could you have two answers that are correct? Not on this, right? Unless you had something like, you know, A and B, B and C, C, you know, that kind of junk, right? So what did y'all say? Oh, man. It's really this one, but I don't want to grade it because so many people got it wrong. I really don't want to grade it. All right, let's see. Let's do another one. For this, take out a sheet of paper and a pen. Take out a sheet of paper and a pen, any paper and pen. Any paper and pen. So you're going to select the correct products for the chemical equation of the hydration of Na3PO4. So what you do is you put it inside of water and you tell me what happens to it, right? Put it in water and tell me what happens. What happens when you put a solid into water? It's going to what? Disassociate. It's going to disassociate. What does it disassociate into? I'll give y'all till 2 minutes for this one. 2 minutes. Ten seconds. All right, so, okay. So what do we disassociate into? We disassociate into ions. If we have Na3PO4, let me see if I can move that. No, I really can't. Let me move it down here. Na3PO4, solid, and water. So we need to figure out what's going to happen. So how do we know what this substance does? Na3PO4. What is this 3? Why do we have 3 Na atoms, 3 sodium atoms? Because the charge on the PO4 must have been 3 minus. So what does that mean the charge on Na is? It's a 1 because there's a 1 here. So it must be 1 plus or plus 1, right? So then what are my products down here? Well, I'm going to have Na, and it's going to be a plus, but we have to say it's in water. So we say aqueous. Then we're going to say this PO4 is a polyatomic ion, right? So we have to leave it together. Don't break it up. If you find it on the polyatomic ion table, don't break it up. It likes it. Don't break it up. Don't make it sad. It's just mean, okay? 3 minus, not a 3 plus. It's like the eraser shows up and then it doesn't erase. I don't understand. 3 minus. Okay. So what are we missing? Yeah, we didn't balance it, right? So we have 3 sodium over here. We only have 1 here. So we need to put a 3 here, and now we're balanced. So what should your answer have been? It should have been this one. So this is why I say take out a sheet of paper and do it yourself. Did we say B? Yes, we said B. Okay. Because you're better off writing your own answer and then comparing it to the answer choices rather than looking for it. It helps you. Okay. Next. All right. Dimensional analysis. Here we come. A common anesthetic comes in IV form as a 2.5 gram per liter solution. What is the concentration of this solution in milligrams per deciliter? I'm going to do you a favor here. In 1 liter, how many deciliters do you have? Could you look on your equation sheet? Not 100. It is 10. It is 10 deciliters. Okay. And then my other one, do I know in 1 gram how many milligrams I have? 1,000. All right. Minute and a half. If Reef isn't letting you answer, close your device, like close it all and then reopen it and see if that fixes it. Sometimes when y'all leave it open, it has trouble. Ashley, you're having the same problem? Good. Oh, I'll give you 10 seconds. This is your 10-second warning. How many people we have today? I thought it was like 40. Okay, so what happens? We're going to start with 2.5 grams in 1 liter. We want to get to milligrams per deciliter. So we're going to convert, let's do grams first. In 1 gram, we have 1,000 milligrams, so our grams cancel. Then I know in 1 liter, I have 10 deciliters. My liters cancel. I'm in milligrams per deciliter. So I just got to cancel my zeros and move my decimal place 1, 2, 250 milligrams per liter. So it should have been D. What do we got? All right. Very nice. Okay. Let's see. All right. Now, this one, I'm hoping you watch the videos. Y'all need to be watching the videos before class. Okay. So what mass of sodium chloride, NaCl, in grams is present in 0.5 liters of a 9% NaCl solution used for IV therapy? Where could I go for a formula that would be really important? It's my equation sheet, right? So what equation am I looking for? I'll help y'all out if you answer. What equation am I looking for? So a percent, and this is in grams and liters, so this is a mass by volume. So what's my formula for this? That's a dilution. This is percent. Grams of solute per, be careful, it's mass per volume. Milliliters. Grams of solute over milligrams solution. Okay, I'll give y'all a minute. So at 2 minutes, 30 seconds. Aiden, trying is better than not trying at all. Always better to try. I'll give y'all till 3.5 minutes. I see a lot of people still haven't selected an answer yet, so I'll give y'all another minute, and I'm calling it. Okay, 10 seconds. Okay, so all you have to do is come in and plug in your answers, right? So I already know the percent. I have a 0.9% solution. Do I know my grams of solute? No, it says what mass in grams. We don't know that. That's our unknown. You put it as X or whatever you want. How many milliliters of solution? Yep, so you got to be careful that this is 0.5 liters. You need it in milliliters. So in 1 liter, you have 1,000 milliliters, which gives you 500 milliliters. Okay. Times 100. So all I'm going to do is cancel my zeros, right? So it gives me 0.9 is equal to X over 5. So 0.9 times 5 is 4.5 grams. Is that what y'all got? What did y'all? Yeah, you were just off on zeros. So be careful with those zeros. Got to make sure that you have the right unit there, because that'll give you a different answer. All right, one more. Well, no, actually, I'm going to save that for next time. I'm calling it on this one. Okay, so let's go do some problems. Let's go do some problems. Aren't y'all excited? Make sure you have your calculators out, because you will need them. You will absolutely need them today. All right, 8.23, I believe is what we were on. And I, for some reason, posted the blank one and not the one I did in the video. So my answers for previous ones aren't there. But I posted, because I got one of the ones wrong. I solved it. My math, I didn't write in everything correctly, but I got the right answers. So I solved 8.23 and 8.24 in a video. So I'll do 8.23 right now, but then the even one's in the video. All right, so we have, what is the concentration in millimoles per liter of a Ca2+ solution? This is our goal. that is 2.50 milliequivalents per liter. So that's what we're going to start with. 2.50 milliequivalents per liter. So now, remind me what an equivalent is. Yeah, there's not so many people in here. It does. It has to do with the charge. So like the intensity of the charge, right? So you can have 1 mole of a substance, and if it has a charge of 1, then it has an equivalence of 1, right? But if you have something that has a charge of 2, it has an equivalence of 2, right? So if I want to convert from milliequivalents to millimoles, all I'm doing is changing from equivalents to moles of Ca2 plus. How many milliequivalents are in 1 mole of calcium? 2. It has to do with the charge. It all has to do with the charge. So whatever the charge is, that's what you're going to put as your milliequivalent. Okay, and I want it millimoles per liter. Okay, I'm in my goal unit. So 2.5 divided by 2 is 1.25 millimoles Ca2 plus. Good. All right. But I am supposed to be doing the even ones, not the odd ones. Yeah, y'all could have told me that. No, y'all just like to watch me. All right, the even ones, the even ones. All right, so 100 millimole per liter is what we're starting out with. We want to get to milliequivalents per liter. I guess I ended up doing them both anyway, right? So in 1 millimole of Mg2 plus, what do I end up with? How many milliequivalents? 2, right? So that's where the 2 comes from. 100 times 2, 200 milliequivalents per liter of Mg2 plus. Okay, even ones, Dr. B, even ones. What is the molarity of 750 milliliters of solution containing 2.10 moles of Na2SO4? So this is our goal. I'm starring this because this is really important. What are the units for molarity? Moles per liter. What's another way that we can write moles per liter? Big M. That's molarity. You have to know this. Okay. All right, so we know that we're starting out with 2.10 moles of Na2SO4, right? And we have 750 milliliters. How do we convert to get to molarity? So all we have to do is convert from milliliters to liters and we'll be in moles per liter, right? So that's it's just a dimensional analysis problem and all you're doing is changing units, right? So if I have 1,000 milliliters in 1 liter, my milliliters cancel, I'm now in moles per liter. So what do you get? 2.8 moles per liter, or we could also say 2.8 molar, and then you always put your substance, Na2SO4. And do y'all know that one of my favorite sounds in the world is the clicking of a calculator? So when you're in class, please do the problems on your calculator. Trust me, the more you do them, the better you're going to get. I promise. Y'all knew I was strange, but you didn't know I was that strange, right? All right. What is the potassium ion molarity? So this is moles per liter of an 850 milliliters of blood plasma containing 10 millimoles of potassium ion. All right. So we're trying to get to molarity. We're told we have 10. Why did they put a decimal point there? Just for significant figures so that we can use two significant figures. Millimoles, K plus, and we have a total of 850 milliliters of our blood plasma. Okay, so now we have to convert two things, right? We're in millimoles and we're in milliliters. So I know I have 1,000 millimoles in 1 mole, and I know I have 1,000 milliliters in 1 liter, right? So my millimoles cancels, my milliliters cancels, I'm in moles per liter. But what do you notice? This cancels with this, right? So this is the same thing as 10 moles over 850 liters. The same thing. What do you get? 0.0. That's not, am I looking? Oh, I'm looking at the wrong one. I always try to look. 0, 1, 2. Hello, hello. Why? 1, 2 moles per liter, or 0.012 molar. And always put your substance. Okay? All right. Now this one gets a little bit tricky. How many grams of NaCl, here's my goal, must be added to water to create 2 liters of a 0.54 molar normal saline solution? What do we want to start with? Doesn't actually matter which one you start with. You could start with either the 2 liters, or you could start with the 1.54 molar. Doesn't make a difference. Okay, 1.54 molar. Hayden's got y'all covered. But instead of saying molar, what are we going to say? Because when we do dimensional analysis, we want to see those units. So instead of saying molar, we're going to say moles per liter. I'm in moles. How am I going to go from moles to grams? Yeah, I got to go to the periodic table and I got to go get my atomic mass. So if I go to my periodic table, what I have to do is I have to look at each of my elements and look at how many atoms of each element I have. I only have 1 of each, so it's super easy. So what's my mass of sodium? My mass of sodium should be 22.99, right? And we only have 1 of them. Then we're going to add that to our chlorine. Our chlorine's what? We only have 1 of them. So what's my molar mass of sodium chloride? 0.40. Is it 44 grams per mole? That's the unit for molar mass. So I want to cancel out my moles. So I know in 1 mole, I have 58.44 grams of NaCl. Am I in the unit I want? I'm in grams per liter. Is that what I want? No, it's not what I want. What do I want? I just want grams. So how do I get rid of liters? What's the other thing that I didn't use yet? 2 liters. Now be careful and put your liters where your liters cancel out. So do liters go on top or on bottom? On top. So my liters will cancel. Put it in your calculators. Let me hear that clicking. do you get? And I think we got 2 sig figs, so rounds to 18. Okay, that's probably one of the trickier ones. Really is. All right, calculate the percent mass by volume for the solute in each of the following solutions. So before we even tackle this, what's my formula? Percent mass by volume is equal to over milliliters of solution times 100. So this is just like what you did in the clicker question. So in this case, I'm given my grams and my total solution volume, and now I'm trying to solve for my percent. So this is my percent is my goal or my unknown, right? So A, we have our percent mass by volume is equal to grams. So this is 75 grams of our solid Na2SO4 divided by milliliters of our solution, 250 milliliters. So our percent, times 100. Mass by volume is what? %30 mass by volume Na2SO4. Okay. B, we're going to do exactly the same thing. It's the same formula, same setup. We're still solving the same thing. This time we have 39 grams of sucrose and 355 milliliters of our solution times 100. Times 100. So what do we get? And y'all are on the ball. Mass per volume, you should have gotten 11% sucrose. 11%, that's right, mass per volume, because it could be different. So you always want to say it's mass per volume sucrose. To CRO. Okay. So do you have to memorize these formulas? Nope, nope. Don't memorize things you don't need to memorize. Just know where they are and know how to use them. Okay. All right. What is the concentration in percent mass by mass? What is mass by mass? Grams of solute over grams of solution times 100. Mass by mass. Okay. All right. So we're trying to solve for the concentration in percent. So that's our unknown, percent mass by mass. We have 10 grams of KCl, right, with 100.0 grams of water. Okay. Is that right? Be careful. Anybody have an idea? I'm telling you it's not right. What did I do? This is grams of what? So this is 100 grams of water plus 10 grams KCl, which will give me 110 grams of solution. Okay, so like, let me rewrite that over here because that just got to be a mess. So your percent mass by mass is equal to 10 grams of the KCl over 110 grams solution times 100. So be careful with that. Just be careful with that because it said water. It didn't say solution. Yep. So what did you get? 9.09 mass percent mass by mass KCl. Yeah, that's a tricky one. It's a tricky one. Okay. All right. How many grams of NaCl must be combined with water to prepare 500 milliliters of a 0.9% mass by volume physiological saline solution? I'm telling you that this is something you need to know. There are two things that make up a physiological solution. One of them is being 0.9% saline. So that's salt, right? NaCl. What's the other? To be physiological. Is 0.0, not 0.0. Oh, 90% NaCl. And then Hayden, no, who's got that? Caitlin has 5% dextrose. Right? So you need salt and sugar in your plasma. You need it, right? So if you're going to make something to where you can give it in an IV and you don't kill the patient, you need to make sure that you have salt in there at 0.9% and you have dextrose or sucrose. You can do different sugars, but it has to be a 5% sugar. Okay. All right, so how many grams? Our question is how many grams of NaCl? Just use your formula. Percent mass by volume is equal to, we're trying to make a 0.9. We don't know our grams of NaCl. What do we put on the bottom? 500 milliliters of our solution. So we'll plug it in. What do you get? 4.5%. So what I do is I just cancel my zeros, right? And then 0.9 times 5. I always love canceling zeros. Makes your math easy. All right. Oh, here's another thing you'll need a formula for. What's the concentration in parts per million of a solution containing 1.5 milligrams of copper and 100 milliliters of tap water? When you're looking at concentrations of things, right? When we say percent, that's parts per what? Parts per 100. So it's part of a percent, right? We're always out of 100. So when you give a percent, you're really giving parts per 100. So what's bigger if I had 1 part per 100 or if I had 1 part per million? 1 part per 100 is going to be more stuff than 1 part per million, right? What about 1 part per billion, right? That's going to be even less stuff. So typically we use percent because that's like physiological, right? But there are times when you just need a little bit of something, and that's parts per million. And then there are some times when you need, like my fingers, you can't even see the distance between them, right? A tiny amount, and that's parts per billion. Okay, so I really want you to be able to keep that in mind. Like, why would you need to use parts per million? Why would you need to use parts per billion? But do you need to remember formulas? No, right? You go to your equation and tell me, what's my equation for parts per million? Times a million. So many. Okay, so our grams of solute divided by milliliters of solution. Don't memorize these formulas, just know where to find them. And they're kind of clustered, which is pretty nice on that equation sheet. All right, so parts per million. We have, what's the problem? We're in milligrams. So we have 1,000 milligrams in 1 gram. What do you get? Right, 1, 2, 3. So then you plug that in, 0.0015 grams. Over milliliters of solution, I have 100 milliliters of solution, and I'm going to multiply times 1,000,000. What do you get? 15 parts per million copper. Y'all got it? Not so bad, right? Really not bad. All right, dilutions. Dilutions is not bad. It's really, really not bad. There's one formula that you need. What is that one formula? CI VI equal to CF VF. Now you might have learned it M1 V1 M2 V2. Anybody learn that one? It's the same thing. You can use either one. It doesn't matter. It's the same thing. Your book uses initial and final. Doesn't matter. But why could you use M? Why would we want to use M? What does M stand for? Not mass. Look at the big M. It's capital M. Molarity, moles per liter. But the thing is, you don't have to be in moles per liter. You could be in any concentration unit as long as the concentration unit on this side is the same concentration unit that's on that side. You could use any volume unit as long as the one on this side is equal to the one on this side, right? So that's why the book uses the C instead of the M. All right, so how many liters of a half normal saline solution with a concentration of 0.5% mass by volume can be prepared from a 1 liter of a 9% mass by volume stock solution? So use your formula. How do I know what is final and what is initial? Initial is always going to be your stock. Your stock is going to be very high concentration. Right? Think about, is it cost effective to store a massive volume of diluted stuff inside of a hospital? Like, do you have the space for that? Not really, no. Space is pretty much at a premium. So what you do is you store things in a smaller volume, but you make them more concentrated. And when you want to use it, you dilute it to whatever the patient needs, right? So this is super, super common and very, very, very applicable. Okay, so my initial is my stock. So here's my initial. Okay, so I have 1 liter of a 9%. Now I always, always, always put my units to make sure that my units cancel out. I have a 1 liter. Now my final, I want to be 0.45% mass by volume, and I don't know what my volume final is. So let's hear those calculators. I even like my calculator on my phone to have the sound of a calculator. I really do. One of those things. You're doing it. What you get? 20 liters. And I would put a point so that I know that that's 2 sig figs. 20 liters. Yep. Okay. All right. So a patient order requires 1 liter of a 0.5 benzalkylum chloride antiseptic. You have a 12% stock solution. How much stock solution will you need to prepare the order? All right, so I'm going to look. Here's my stock. This is my initial, right? And here's my final. So now I just need to plug it in. C1, CI, VI, CF, VF. So my initial is a 12%, right? And this is why we can do this. As long as the units are the same, if it's percent on one side and it's percent on the other side, it's fine. We don't know my initial volume because we don't know the stock volume that we need, but we know we want to make a 0.5% and we know we want it to be a liter. So what do you get? Something small? Okay, 0.042 liters. Yeah. So how do you measure 0.42 liters? If you're in the lab, like you're preparing this order for somebody, what do? Convert it to milliliters. So I know that 0.042 liters in 1 liter, I have 1,000 milliliters. So that is what? 42 milliliters. Can you go in and measure that? Yeah, you can use a graduated cylinder or whatever it is to measure that. So the question didn't ask me for milliliters, but what if on an exam, I give you some choices that are liters and the numbers aren't right, but I give you an answer choice in milliliters. And if you do the conversion, the answer choice is right. You have to make sure that you can do that because sometimes you're going to get a unit that you actually can't measure. Like what measuring device is going to measure in liters? No, you don't want to do that. You want to measure in milliliters, right? So I want you to kind of be aware of that. Okay. All right. Here we go. How would you prepare 2 liters of a 1 molar MgCl2? So I'm preparing this. So this is my final from a 5 molar MgCl2 stock. This is my initial. So CIVI, CFVF, my initial 5 molar. I don't know my concentration. I don't know my volume. I know my concentration of my stock was 1 molar, and I want to make 2 liters of that. So what do you get? What do you get? 0.4 liters. What's another way to say that? $400 milliliters, right? If you want to measure it in the lab, I want to measure 400 milliliters of my stock. Now, be careful. This says, how would you prepare? So tell me, how would you do it? What would you do? It's a little tricky, right? Now, can I say I'm going to add this much stock and this much water? I'll tell you that sometimes when you add 2 solutions together, 2 liquids together, it's not a perfectly additive effect. So let's say I wanted to make 100 milliliters of something and I add 50 and 50. Sometimes when I mix it together, because of solubility, I'll get 95 mils. So my concentration would be off. So when you make solutions, this is how you do it. You take your stock first. So you would add 400 milliliters of my stock, 5 molar MgCl2 to a, could be a flask, could be a graduated cylinder, could be whatever device you're measuring with, right? To a flask, we'll say, doesn't matter. And then what am I going to do? Now I'm going to pour enough water to bring that volume up to my final desired volume. Then add enough water to reach 2 liters. Right? Because sometimes it's not perfectly additive. Or sometimes it's you're dissolving a solid and you put a solid in and you think, okay, I'm going to weigh out, 20 grams of this solid and I'm going to make a liter. So I have a liter of water and I put 100 grams of my solid into my liter of water. What is actually going to happen? I'm going to have slightly more than a liter because it's going to change the volume. So you always put your stock or your solid, then add water to fill to whatever your final volume is. Okay, now we're doing dilutions. There's a formula on your equation sheet for dilutions. What is that formula? Your dilution factor is equal to VF over VI. You can use that. But I think it makes more sense, and I'll show you how to use that, but I think it makes more sense to use the concentration formula we've been using, right? So if I have a stock container, and I tell you, here's your stock container, I want you to make a 1 to 8 dilution of it, right? What does that mean? That means that my stock was an 8x solution, and my final volume, my final container is going to be a what x? If I say make a 1 to 8 dilution, that means my stock is 8x, my solution for my patient is 1x, right? That's what a dilution is. Like if I said I had a 100x stock, now make me a 1x solution, that's a 1 to 100 dilution. That's what dilution means, right? So you can plug this into your C1 CI. I always want to say CI. C1 CI VI equal to CF VF, right? So you could say my concentration of my stock is 8 times. I don't know why it does that. Like it's a bit of a delay. Is 8 times as concentrated as what I want it to be. That's a 1 to 8 dilution. And then all I have to do is plug in my formula. I want 400 milliliters of my final. Well, what's the initial volume that I need? So just divide by 8. What do you get? 50 milliliters. Now let's see if that works in our formula, right? So our dilution factor is equal to VF over VI. So what's my dilution factor? 1 to 8, or 8, you're diluting it 8 times. What's your VF? 400 milliliters. And then I don't know my VI. So what do you get? Just cross multiply. Same thing, right? Doesn't matter how you slice it, it's the same thing. All we're saying is that you can do this because this is a 1. You know, I think y'all can handle that. I think it makes more sense this way, but they didn't really ask me. Okay, so Osmosis and diffusion, right? Okay, so when you talk about osmosis and diffusion, there are three really important terms. Those terms are hypotonic, hypertonic, and isotonic. You remember what that means? This is my cell. I'm going to draw three different. Okay. So if something is hypotonic, which way is water going to move? Into the cell or out of the cell? Into the cell. How do we know that? Did y'all watch the little video? There's more solute, but I like to have a little trick. So my trick is, here's my pot. If I want to cook, what do I have to put into the pot? Water. So if I see pot, I'm going to know that water is going to go in, right? Because I have lots of solute particles inside of the cell, lots and lots and lots and lots and lots of them, and I only have a few outside. So water is going to travel to basically areas of higher solute concentration. So it's going to enter the cell. Okay. Now, what happens if I'm going to be here for a long time, right? Lots and lots and lots and lots outside, but only a little bit inside. What's going to happen? The opposite, right? Our water is going to leave the cell and it will shrink. This one will swell. Okay. So what do we call it when water moves out? Hypertonic. Okay. How do you remember that? Look at this purr. What purrs? A cat purrs. Right? It's got whiskers. Y'all know I'm a great artist. Y'all didn't know that about me, right? I cannot draw a skinny cat. I just can't. Not possible. Okay. So what sound does he make? He purrs and it comes out, right? So the water comes out. Okay. What's my last one? Isotonic. So I have a similar concentration of solutes inside and outside. So this is isotonic, right? And nothing happens. Well, not nothing happens. Honestly, actually, the same amount of water leaves as enters. So you have no net change. Okay. So this is no change in cell size. Make sense? Okay. So sometimes it's just nice to like write that out before we try the problem. Okay, we have a lettuce leaf in the produce aisle at the grocery store is accidentally submerged in water. Oh, can you believe it? Will water exit or enter the lettuce cells? Did we put it in salt water or did we put it in basically pure water? Basically pure water. So it's going to look like this, right? Your lettuce cell has stuff on the inside. All cells have solutes on the inside. We're going to put it into water that doesn't have a whole lot. So what's going to happen? Water will enter the cell and the cell will swell. And is this hypertonic or hypotonic? Hypo. Right. Once you kind of do that, it's easy to answer. But if you just look at it without jotting those things down, sometimes it can get really confusing. Okay, a patient is undergoing hemodialysis. Why do patients undergo hemodialysis? They have kidney failure. What's the job of the kidneys? To filter the blood. So somebody who has to go on dialysis, they can't filter their blood. So all of the waste particles, the waste that all of your cells make all the time, can't come out of your blood. So this person has high solute concentration in their cells. So not in their cells, in their blood. In their blood. Okay, so the whole point of dialysis is to take out their blood and mix it with a dialyzing solvent, right? So you have the blood on this side, the solvent over here, and then you have a membrane. Because you want to keep the red blood cells and the important bits in their blood, but you want the waste products to basically diffuse over, right? That's the whole point of dialysis. So as blood leaves the patient, it has blank osmotic pressure. What's going to control osmotic pressure? What happens if you have a lot of solute particles? Water wants to what? Go towards it and dilute it, right? So you can have a lot of water there. The more water you have, the higher the osmotic pressure, right? So you're going to have a higher osmotic pressure than the dialyzing solution. As the blood re-enters the patient, so we've gotten rid of all the waste, the osmotic pressure is what versus the dialyzing solution? Remember, those solute particles are going to move to areas of high concentration to areas of low concentration. Think about, you've seen those little like packs of like Crystal Light, the little ones that you put in your water container, right? If you pour it in and you don't mix it, eventually it will mix, right? And eventually you'll get a homogeneous concentration of Crystal Light, right? The same thing happens in dialysis. You're going to have those waste particles diffuse over until you're what? Homogeneous, all the same. So what's going to happen is that you're going to have the same number of particles in the blood as you do in the dialyzing solution. So how is the osmotic pressure going to be? Higher or lower or the same? Got to be the same. Got to be the same. The same. Good. All right. Let's see. Okay. Now, we have a red blood cell. We're going to give a patient an IV of fluid and of these following solutions. And what's going to happen to that cell? Is it going to undergo crenation? What is crenation? Another word for shrink. Lyse is swell and burst, and then no change. Okay, so how do I decide if a cell is going to shrink or burst? What do I need to know? Feels like they're missing a bit of information here. We're at physiological solutions. So our red blood cells are normally in what? 0.9% NaCl and what? 5% sugar, glucose, we'll say. Come on. See, it just, I've written it like 3 times. Glucose, right? Okay, so what if I put, here's my stuff, here's my cell. I'm at 0.9 NaCl, and I'm at 5% glucose. What if I put this cell in something that is 10% NaCl? What's going to happen? Remember, water is going to areas of higher solute concentration. Water moves to areas of high solute concentration. So what's going to happen? So it's going to move from 0.9 to 10. So water is going to go out. What happens when water goes out? It's going to shrivel up. That's right, it's going to shrivel up. And so this is crenation. Okay. Now, come on. Now what's going to happen? Let's see. We got distilled water. What is distilled water? If you distill water, what are you trying to purify out? All kinds of stuff, right? We're trying to get pure water. So we have like this water with stuff in it. And so we boil it. The water evaporates. We collect the evaporated water, and all the junk that was in the water is left behind. So basically you're saying you're about 0% everything. Right? We're not quite, but pretty close. So what's going to happen? Water is going to flow to areas of high concentration. Which way is water going to flow? I have 0% and then 0.9 and 5%. So my water is going to go into the area of higher concentration. So what's going to happen to my cell? It's going to swell and then burst. So lysis. Does that make sense? So always put your arrow for your water going to whatever's higher concentration. Okay, let's see if I can erase this. It's getting kind of junky looking. All right, I have 5% NaCl. What's going to happen? Same thing, crenation. We're still going to go from areas of low concentration to areas of high concentration. 5% still higher than 0.9. So we're still going to have crenation. Okay. And then the last one is 5% glucose. No change. No change. Because our glucose concentrations are the same. All right, transport across the cell membrane. Now, when we talk about transport, if you're going to undergo passive diffusion, what direction is going to happen? This is a membrane. What direction are these molecules going to diffuse? These are oxygen molecules. Left or right? So are they going to go this way? Or are they going to go this way? They're going to go to the right. They're going to go from areas of high concentration to areas of low concentration. That's the whole point behind diffusion. So if that's diffusion, you're always going to go from high concentration to low concentration. Okay? So identify the type of transport. Passive diffusion. If this is diffusion, we have to go from areas of high concentration to areas of low concentration. But what are some general characteristics of molecules that can undergo passive diffusion? Like, what is it about O2 in this example that allows it to undergo passive diffusion across a cell membrane? Big or small? Small. Polar or nonpolar? O2 is oxygen bound to an oxygen. Polar or nonpolar? If you have two atoms that have the same electronegativity, do they have a polar bond? No, the definition of a polar bond is differences in electronegativity. So this is a nonpolar bond. So is your molecule polar or nonpolar? Nonpolar. So small, nonpolar. Good. What's my one exception to this passive diffusion? Water. Water can undergo passive diffusion. It's special. But water can also undergo facilitated transport. Facilitated transport is like a tunnel, right? Anybody can drive through the tunnel, right? As long as your car fits through the tunnel, you can go through it. right? So molecules that undergo facilitated transport, there's a pore there that lets them go through. But do you have to like pay a toll to go through a tunnel? No, right? So it doesn't require energy. So this is no input of energy. What are some molecules that would need to use a tunnel? Ions, charged things, charged or polar substances, right? What else? Large or small? Large, relatively large. Okay, how about active transport? What's our key feature for active transport? You need energy. You need energy. So these can be all kinds of different things that are involved in active transport. But a lot of times what's happening in active transport is that you go from an area of low concentration, to, move this over, to high concentration. Is that how diffusion works? No, that's like the opposite, right? Things aren't naturally going to go from an area of low concentration to an area of high concentration. They just don't do that. So in order to make that happen, you have to expend energy and grab them and move them, right? So let's look at our examples and see if we can figure out, now that we've got kind of some ideas. Oxygen, passive diffusion, facilitated transport, or active? Passive, small nonpolar, it's passive. Okay, glucose, no energy required. This is facilitated. What can we say about glucose? Glucose is a sugar. Is it polar or nonpolar? Polar, right? You got all these OHs all over the molecule, right? It's very polar. So it needs a tunnel to get through the membrane. Na plus, energy required. Active. K plus, no energy required. Facilitated. What if I had said oxygen, no energy required? Still passive. By default, passive diffusion requires no energy. E-N-E-R-G-Y. We just don't say it, but it doesn't require energy. It's diffusion. It does it just because of the inherent kinetic activity of the molecule. Okay. Oh, we were supposed to do the even. Y'all. Okay, cholesterol. Let's do these quick because we already defined them real quick. Cholesterol. Big or small? Polar or nonpolar? Remember cholesterol when we drew it? And we drew, and then I had to draw another one. And then I had to draw the little house, right? And then I had to draw like all of these carbon chains. Big or small? Big. And it's really mostly nonpolar. So if it's big and nonpolar, what are we doing? Facilitated. Okay, nitrogen. This is small, nonpolar, so this is passive. Okay, Cl minus, no energy required. This is small and polar, this is facilitated. H plus, energy required. Active. Okay. I think that's the end. So, homework. Homework is due tomorrow night. There are bonus points inside of the homework. Please, please, please take advantage of them. Then we'll start chapter 9 on Tuesday, no, on Thursday, finish chapter 9 on Tuesday, exam on Thursday. It's coming up, so stay on top of this. We're almost at the end. Don't give up. All right, y'all have a great afternoon. And anybody on chat need anything? Okay, I'll go ahead and end the Zoom if y'all don't need anything, and y'all have an awesome afternoon. Oh, I'm typing something. Okay. All right.